Today, we're going to tackle a classic puzzle from electrical engineering, the maximum power transfer theorem. Now, it sounds simple enough, but it hides this really fascinating paradox that trips up even some of the sharpest engineering students. So let's dive in and unravel this thing.
And hey, if you've ever been stumped by this, you are definitely not alone. Just take a look at this post from a very confused student on Reddit. You can feel the frustration, right? They've done the math, they see the result, and it just doesn't feel right. Maximum power is only 50%? It sounds like an absolutely terrible deal.
And that question right there, that gets to the absolute heart of the confusion. It just feels fundamentally wrong. I mean, why would any engineer in their right mind design a system that intentionally throws away half the energy it generates? That is the central puzzle we're going to solve together. To solve this, we've got to break it down, and the best way to start is by looking at the two extreme ends of the spectrum. It's in those extremes that we'll see why there has to be a sweet spot right in the middle. Okay, first things first, we need a simple model to work with. So on the left, you've got your power source. Think of it as a battery. It has an ideal voltage source, VI, and some internal resistance, RI. That's just the natural resistance from its own internal chemistry. And on the right, that's our load, RL, the thing we're actually trying to power up. Now, the entire game here, the whole thing, is governed by one fundamental rule of physics. Power equals voltage times current. You can't just crank one of them up and ignore the other. To get the most power, you need a healthy amount of both. You need voltage pushing and current flowing. So let's look at those two extremes. On one hand, what if your load resistance is infinite? We call that an open circuit. Well, you'll measure the full source voltage, sure, but the current has nowhere to go, so zero current flows. And what's anything times zero? It's zero. Zero power. Now let's go to the other extreme. What if the load resistance is zero, a short circuit? Well, now you're going to get the maximum possible current, but the voltage across that short is zero. And again, zero voltage means, you guessed it, zero power. So think about it. If we get zero power at both extremes, zero resistance and infinite resistance, then the maximum amount of power has to be somewhere in the middle, right? And this graph shows it perfectly. As we start increasing the load resistance from zero, the power shoots up, it hits a peak, and then it starts to fall off again as the resistance gets too high and starts to choke off the current. So the million-dollar question is, where is that peak? Where's that sweet spot? Well, it happens at the exact moment the load resistance becomes equal to the source's internal resistance, when RL equals RI. And that, in a nutshell, is the maximum power transfer theorem. But, you see, this brings us right back to our original puzzle. If matching the resistance wastes so much energy, why would we do it? This is where we have to untangle the critical difference between maximizing power and maximizing efficiency. They are not the same thing. And this is the absolute key to the whole puzzle. These are two totally different engineering goals. The goal of maximum power transfer is all about squeezing the most absolute watts you can from a given fixed source that you can't change. But the goal of maximum efficiency, that's about wasting as little energy as possible. And to do that, you'd actually want your load resistance to be way, way higher than your source resistance. So let's be super clear about what we mean by efficiency. It's just a simple ratio. It's the power that actually gets to your load divided by the total power the source has to generate to begin with. And remember, that total power has to supply both the load and all the energy that gets lost as heat inside the source itself. And here it is, the big reveal. At that point of maximum power transfer, when the source resistance and the load resistance are exactly equal, they create a perfect voltage divider. Each one gets half the voltage. And since they have the same resistance, they dissipate the exact same amount of power. So half the power goes to doing useful work in the load, and the other half is just burned up as heat inside the source. That's where the 50% efficiency comes from. Okay, so if it's only 50% efficient, that still sounds kind of bad. So why on earth would you ever use it? Let's check out some real-world situations where this isn't just useful, it's absolutely essential. You use this theorem when the power of your signal is incredibly precious, and your source is what it is. You can't change it. A perfect example is a radio transmitter. You want to dump every last possible milliwatt of power into that antenna so you can broadcast as far as possible. Who cares if the transmitter gets a little warm? The goal is range. Same goes for a solar array. You have a fixed amount of sunlight, and you need to extract the absolute maximum power from those panels. And where would this be a totally terrible idea? Well, the power grid.
Can you imagine if half of all the energy from our power plants was just lost as heat in the transmission lines? It would be a global catastrophe. For the grid, or for things like a high-fidelity audio amplifier where you want a clean, efficient signal, not raw power, efficiency is king. Wasting energy is not an option. So what happens when your source and load resistances are fixed and they just don't match? Well, engineers have a really clever tool for this, a transformer. By picking just the right turns ratio, a transformer can trick the source into thinking the load has a different impedance. It's an impedance matcher, letting engineers create that perfect match for maximum power, even when the parts themselves don't line up. Now, everything we've talked about so far has been for nice, simple DC circuits. But, things always get a little more complicated, and honestly, a lot more elegant when we jump into the world of AC.
See, in AC circuits, it's not just about resistance anymore. Components like inductors and capacitors, they create this other kind of opposition to current, called reactance. And when you combine resistance and reactance, you get something called impedance. So now we're not just matching a simple number, or matching a complex value.
The solution for AC is called complex conjugate matching. I know, it sounds really intimidating, but the idea is actually beautiful. The rule is simple. First, just like with DC, the resistive parts of the source and the load have to be equal. And second, their reactive parts have to be equal in value, but opposite in sign. So if the source is inductive, the load has to be equally capacitive. So here's what that looks like in a circuit. Our AC source has its internal resistance, Ri, and an inductive reactance from its coils, XLI. So for that perfect match, our load needs a resistive part, RL, that's equal to Ri, and a capacitive reactance, XCL, that's equal to XLI. And here is where the magic happens. Because the inductive reactance of the source and the capacitive reactance of the load are equal and opposite, they fight each other to a standstill. They completely cancel each other out in the overall circuit. They just vanish, leaving us with a purely resistive circuit. And hey, we already know how to solve that one. Just make the resistances match. It's so elegant. So let's bring this all together. The real key here is to stop seeing this theorem as some kind of flaw or limitation. It's not. It's a highly specialized tool for a very specific job. Look, the maximum power transfer theorem is not a command that says you must waste 50% of your power. It's a design choice. It's the answer to a very specific question. Given this source that I cannot change, how do I squeeze every last possible drop of energy out of it and get it to my load? It's a choice to prioritize raw power over efficiency. And this really leaves us with a bigger thought that applies to way more than just electronics. When you're designing any system, anything at all, what's the ultimate goal? Are you optimizing for raw, absolute power at any cost? Or are you optimizing for precious, sustainable efficiency? The answer to that question? Well, it changes everything.